We know that the Gibbs free energy is a function of the pressure, and the chemical potential is the Gibbs free energy per mole of a substance. So the chemical potential must also depend on pressure. Let's look at that functional form now. As always, we will start with the differential expression. The differential expression for the chemical potential of any component is equal to minus the molar entropy of that component, dt, plus the molar volume of that component, dP. So if we want to know how the chemical potential changes with pressure at constant temperature, then we have the molar volume of that component. If we treat our gas as ideal, then we can use the ideal gas equation of state for the molar volume. So the chemical potential changes with pressure at a given temperature as RT divided by the pressure. So if we want to have an expression for the chemical potential as a function of pressure, we need to separate variables and integrate. So d mu is equal to RT over P dP. If we now integrate from our reference state, standard state of 1 bar, to any other state, at a given temperature, so temperature being constant, we're going to integrate from our reference state of 1 bar to any other pressure, dP over P. We can write that the chemical potential minus the chemical potential in the standard state is equal to RT natural log of P over P standard. So the chemical potential is equal to the standard state chemical potential, the chemical potential at 1 bar, plus a correction for not being at standard state, for not being at 1 bar of pressure. This is then an expression for the chemical potential of a gas. Notice that I've treated the gas as an ideal gas, and this is a pretty good expression for the chemical potential for most reasonable temperatures and pressures because we can treat most gases as ideal at reasonable temperatures and pressures. We will see that in general, we can write the chemical potential of a substance as the chemical potential in the standard state for that substance plus a correction for not being at standard state.